Hello everyone, this is Menucho from Kyushu Institute of Technology, Japan. It is my pleasure to give KiboCUBE Academy online lectures about lessons learned of CubeSat missions. First, let me introduce myself. I have been working at the Kyushu Institute of Technologies, known as QTech, since 1996. Originally, my research area was spacecraft chargings or spacecraft environment interactions. But nowadays, I'm more interested in lean satellites, otherwise called small satellites. These are the pictures of the satellite in which I have been the principal investigators. Since 2012, so far, 20 satellites have been launched into space. QTech is a national university with a history of more than 110 years. The university has 3 campuses focused on science and technologies. We are located at Kita-Kyushu, which is 1,000 kilometers west from Tokyo. In terms of distance, the distance to Korea is much shorter than distance to Tokyo. At the QTech, I have been the director of Center for Nanosatellite Testings since 2010. We are capable of doing all the tests for satellite up to 50 centimeters, 50 kilograms. We open the test facilities to external users who are looking for a place to test their satellites. So far, we have tested more than 70 satellites, including satellites from overseas, such as Egypt, Costa Rica, Singapore, Malaysia, Vietnam, Thailand, and others. In March 2022, the center received Space Development and Utilization Award, a JAXA President Award, in recognition of contributions to the space sectors. At QTech, we are not only testing satellites, but we also build a satellite by ourselves. These are the satellites I have been involved until now. We have launched 20 satellites since 2012. 4 more satellites will be launched in 2022. According to Bright Space and Technologies, which is a consulting company located in the US, QTech has launched more small satellites than any other academic institutions in the world since 2012. Now let's move on to the lectures. The purpose of today's lecture is to introduce lessons learned case of University CubeSat project and how to reflect those into later satellite project to improve the mission success rate. This is the content of today. After the introductions, I'll talk through some of lessons learned cases and their root causes. By knowing the root causes, we can reflect the lessons to the later project as a part of mission assurance activity. First, let me introduce University Satellite Project in Japan. In Japan, many universities who carry out satellite projects belong to the University Space Engineering Consortium, called UNISEC. UNISEC now has a local chapter worldwide at UNISEC Globals. UNISEC Japan consists of 36 universities and research institutions, 49 organizations, 636 student members, and 262 individuals, and 19 corporate members, and alumni members based on April 13th statistics. UNISEC Japan's members maintain cooperative relationships in conducting practical space development and utilizations. These are satellites developed by UNISEC Japan's members universities up to 2019. There are more than 50 satellites developed and operated. In 2020, due to the pandemic, we had a lot of free times, not being able to go to work or travel. members of UNISEC Japan came up with an idea of using free time or something productive. We had remote sessions on lessons learned from University Satellite Project in UNISEC. During the remote sessions, more than 20 professors talked about the lessons learned from their own project. Everybody talked honestly about what they really went wrong, how they could have prevented it, but failed to do so, how they implemented the lessons to the next project, and so on. It was really a good way of using the free time during the pandemic. Later that year, we talked to JAXA about these lessons learned activities. JAXA said it is a very good activities and offered some sponsorships to promote the activity further. With the JAXA sponsorship, we completed a survey on lessons learned in terms of mission assurance and made a 439 pages report. The report is about analysis about success and failure causes of domestic, micro, and non-satellite projects and their causes, and extractions of requirement for mission assurance of micro and non-satellite. Following the activity in 2020, in 2021, UNISEC members worked on a mission assurance handbook for university-based lean satellites. We did further analysis of the failure caused by conducting intensive interviews with the persons in charge of each project. Based on the activities, Mission Assurance Handbook for University-Built Lean Satellite was published in March 2022. These lectures will provide examples of lessons learned cases, the failure root causes, and how to improve the mission success rate. By the way, this Mission Assurance Handbook also has English versions. Now let me introduce some examples of lessons learned and the root causes. I first describe the problems encountered in orbit. Then I explain the root causes of the problems of each case. The first case is a 3U CubeSat. In this case, the satellite was built. A satellite was very difficult to assemble. Every instance where the satellite was assembled for testing, it suppressed the schedule significantly. Also, during the safety review, the team promised JAXA to do a 3D measurement each time the satellite was assembled. Another lesson was that the software development progress was far behind the hardware development. After the launch, the satellite encountered a mode of resetting in an infinite loop due to collision of I2C signals. The team couldn't communicate with the satellite for more than 1 year. The root cause of this case is the following. First, the team promised more than enough for the safety requirement verifications, which was a 3D measurement after each satellite assembly. It consumed a significant amount of time. Next, the student motivations played a factor. Only a faculty member were involved in the mission definitions, making students think this is the professor's satellite, not ours. The schedule management was poor because it was the first satellite of the team. Due to the schedule delay, a long-term end-to-end test was not done, overlooking the issue of I2C collisions. Finally, the satellite structure was too complicated, which comes from the lack of experience in satellite design. The second case is a 1U CubeSat. After deployment, no signal from the satellite was received by the ground station. This is referred to as DOA, Dead on Arrivals, which is the worst mission failure. Because there was no telemetry at all, the exact cause of the failure is not clear. But there were many single points of failures in the satellite design. One possibility was connecting the solar cells incorrectly by mistaking this bypass diode tab as an electrode. This type of solar cell is called integrated bypass diode functions. There is a tab that looks like an electrode, but it is an electrode connected to the diode in parallel to the solar cells, not connected to the solar cell itself. For this case, also, the satellite delivery date was fixed because it was launched as a part of the free launch campaign by JAXA. The satellite had to be delivered regardless of its conditions. There was not enough time to do the testing. The root cause of this case can be attributed to the fact that it was the first satellite of the team. They didn't know what to do to build the satellite. They didn't even know where to seek help or who to ask when they had a question. The third case is a 2U CubeSat. In this case, ground stations could receive a CW beacon, but couldn't perform the uplink. Overall, the ground station preparations was insufficient. Checking of its functionality was not completed using other satellites in orbit, nor was the overall link budget verifications was not done correctly. The university team was from the mechanical engineering department. Therefore, they lacked the necessary know-how for the communication. To fill the gap, the teams depended on external supporters regarding the communication system. It is okay. Thanks to external assistance, communication hardware was made, but it was difficult to point out the problems during the system test that was done at the university because of the lack of communication expertise at the university side. The root cause of the failure was that the team depended on the amateur radio expert outside the campus for the communication subsystems. The communication between the expert and the student was difficult due to physical distance. The principal faculty couldn't take care of the gap properly. Where there is a lack of necessary expertise for the satellite project, it is very difficult to achieve mission success. The fourth case is a 50 kilograms Earth observation satellite. The satellite power budget did not have enough margins. Because of a power shortage, frequent satellite reset occurred. Every time reset occurred, the attitude control history was overwritten, and the complex attitude control sequence had to be restarted once again. It took much time to establish the proper attitude for the mission success, as a camera capture and high-speed downlink. Because of the insufficient attitude controls, no image data could be downlinked until the end of satellite mission. Similar to other failure cases, the satellite was the first satellite for the team. The team lacked experience in satellite system design, development, and operation. Because of a lack of experience, they couldn't properly perform schedule management. There was no time to do the full system test to check the power budget under the flight representative conditions. A very important word in satellite testing is test as you fly. But the team couldn't do it. The fifth case is another 50 kilograms Earth observation satellite. In this case, the battery was not designed to stop charging once it was fully charged. Because of this, a very delicate charging maneuver in orbit was necessary. In addition, there was no bypass diode or blocking diode in the solar cell circuit. With the shadow fell on the solar panel circuit because of a deployment of an extended mast. It killed the entire solar array circuit on 50 centimeter panels. Due to the sudden drop of power generation, the battery voltage decreased significantly as the delicate charging maneuvers no longer worked. The overall satellite bus voltage decreased, then the satellite FPGA became a zombie state, neither alive nor dead, which it cannot function nor rebooted completely. Again, this was the first satellite for the team. The team didn't have enough experience to check the design made by the EPS contractor. They blindly trusted the contractors because EPS contractors had experience in many satellite projects. Also, the team didn't have experience of doing system tests. The eighth case was a 7 kilograms education tech demo satellite. It was the first satellite for the university teams. The satellite deployment was successful, and housekeeping data was collected for initial 3 weeks from deployment before executing the mission. When the team finally moved to send a command for the main mission, the communications with the satellite was suddenly lost due to single event latch-up, in short, SEL. Fortunately, the satellite recovered with a power reset, but the operation time was severely limited due to a series of disruptions caused by SEL. To recover from SEL, the satellite was equipped with an overcurrent protection, OCP, but it didn't work due to inadequate settings of the threshold current. The threshold value was set at 500 milliampere, but the actual latch-up current was 200 milliampere, as shown in the figure below. This shows a case when satellite recovered from a latch-up. So this was during the latch-up. This is normal state. So in a normal state, it's about 50 milliampere. But in a latch-up state, it's more than 200 milliampere. So if they set the threshold to 200 milliampere, they could detect when latch-up occurred and activate OCP and recover from latch-up, but they couldn't. The root cause also was the lack of experience in radiation mitigation design. The overcurrent protection circuit, this threshold value was decided without any basis. The single event latch-up protection was designed but not verified. The teams just assumed that it would work without any basis. Every design should be verified. Another important lesson was that the team should have done the main missions earlier without looking at the satellite telemetry for the initial 3 weeks. For a university small satellite in orbit, anything can happen at any time. We should do the main missions as early as possible to achieve the minimum success levels before anything happens to the satellite. The ninth case was a constellation of 5 1U CubeSat. All 5 satellites had an identical design. Each satellite carried an experimental patch antenna for both downlink and uplink. The downlink uses UHF and uplink uses VHF. It turned out the gain of the patch antenna was not as good as expected. CW beacons that use UHF was very weak. Uplinking using VHF was not successful for all 5 satellites. The problem was not detected by the ground test because the flight model antenna arrived at the last minute and no system communication test was done with the flight model. So the root cause of this failure lies very deep in the project management. First of all, the satellite design attempting demonstration of new technologies, patch antenna, was inconsistent with the satellite mission, which is education. The team also lacked expertise in communication technologies. They couldn't properly understand the risk of a patch antenna. One reason of choosing the patch antenna was to avoid the risk of antenna deployment failure. It may have been a good reason if there was only one satellite. But the team should have considered the advantage of constellation more. They should have selected a strategy of making at least one satellite survive, rather than making all of the 5 satellites survive. Moreover, key decisions of using patch antenna was made only by the principal faculty. No other member could challenge the decision. The principal faculty should have created an environment that anybody, even if a beginner in satellite design, could voice out any concerns whenever they feel it necessary. The last case was the constellation of 3 1U CubeSat, which is the next project of previous 1U CubeSat. This time, a patch antenna was not used. Instead, a deployable monopole antenna was used. The UHF beacon, it was improved drastically. But the uplink suffered difficulties due to internal noise generated by EPS pool. The problem was not detected during the ground test because the internal attenuators of 10 dB in a reference dipole antenna was overlooked. This resulted in overestimation of 10 dB in link budget. The root cause was in the team expertise. There was only one person who was good at communication. All the tasks related to the communication went to that person. Other team members couldn't check the test setup consistently. That is why they overlooked the 10 dB internal attenuator. Another cause was a lack of knowledge that internal noise affects uplink signal reception. When the link budget was calculated, the background noise was chosen without any basis. In a CubeSat, because all the electronics boards are closely packed, coupling of noise is very significant. The uplink signal is very weak when it reaches the satellite, but it still has to overcome. We still have to overcome the background noise. So the signals must be stronger than the background noise. The link budget must be verified by the communication test using the flight models operating in flight representative conditions. That is the only way we can verify in a CubeSat, which is very small and noise coupling is too complex to do by analysis or other means. Now let me talk about the mission assurance. In the lessons learned shown as examples, there are many common causes among different cases. They are poor schedule management, insufficient team, talent, and skill, inconsistency in requirement, improper verifications, plannings, incorrect strategies to avoid total satellite loss, insufficient full system end-to-end testings, difficulty in assembly integration testings, poor understandings of the rationale behind the design, and others. Now let us think about how to derive principles to assure the mission success based on the result of those analyses. Mission analysis is defined as a series of activities to identify the factors in design, makings, operation of the satellite, others, that will hinder mission success and to eliminate or decrease the effect of such factors. At the same time, we should consider that most university satellites are categorized as lean satellite. A lean satellite is a satellite that utilizes non-traditional risk-taking development and management approaches with the aim to provide satellite value to the customer and all stakeholders at a low cost and with a short time to realize satellite missions. For more details, you can see the reference listed here. Lean satellite tolerates risks, but still needs to achieve the mission success as much as possible. So it is not failure is not options, nor failure is accepted. Based on the lessons learned activities and the root cause analysis, we have developed Mission Assurance Handbook for the university-built lean satellite. It is targeted at the satellite project at the universities and polytechnic college in Japan. It covers not only the first satellite project of the universities, but also the second and later project. The handbook lists a summary of points to be kept in mind by faculty members and students to improve the mission success rate. The book is organized in the order of project life cycles. The draft version is complete now, and the final version will be published in late 2022. Although the handbook is targeted at Japanese universities, much of the content is still applicable to satellite projects in new space companies and or non-Japanese organizations. Therefore, an English version has been made as well. These are the contents of the handbook: introductions, project management, mission definitions, conceptual designs, detailed design, productions, testings, operations, post-operations, sustainability of university satellite programs. Chapters 3 to 9 are in order of project life cycles. I will now introduce some of the content. In the chapter of project management, we write about schedule management. It is a fact that first project often fails. Mostly this is due to improper schedule management coming from the lack of satellite project experience. Because of this, very little time is spent in systems test. In this chapter, we write a guideline for project milestone until the satellite delivery. In this case, D is the satellite delivery. 1 month before the delivery, flight model hardware and software should be complete. Hardware testings, such as thermal vacuums, vibrations, and others should be finished already. Basic ground station software should be complete. The 1 month before delivery should be spent in final verifications of flight software by doing long durations system end-to-end test using satellite flight models and the ground station. 3 months before the satellite delivery, all FM hardware components must be delivered. and ready for FM system assembly. This means that the satellite assembly, integration, and testing is finished in 2 months. 6 months before the delivery, the engineering models should be finished. The review is held at this time. In 3 months from this time, the FM hardware component will be procured. So this is a long story when people do CDR. Okay. 10 months before the delivery, all EM hardware components are supposed to be delivered and ready for the system assembly. The assembly, integration, and testing of EM should be 4 months. It is longer than FM phase as more problems are found compared to the FM stage, and it takes more time to fix them. At 13 months before the delivery, the proof of concept should be obtained. The team should confirm that the missions are feasible with more solid evidence, such as breadboard model testings, than a simple analysis on paper. Usually, a preliminary design review is held at this time. Procurement of engineering models should start by this time. For some components, it takes more than 3 months to be delivered. Procurement of such components should start earlier than this D-13 months milestones, especially if you buy components from vendors overseas. How long it will take to reach this D-13 milestone depends on what mission is to be done. The simpler the mission, the shorter the time of this stage. Another important aspect of project management in terms of mission assurance is the team talent. It is not possible to have all the talent necessary for the project conducted by students alone. The team needs to find solutions to fill the shortage. It can be procurement, i.e., we solve the problems by money. Collaborations with external people, such as amateur radio expert for the case of communications. Or we can expect students to grow. Even for 1 or 2, the requirement for the procured or outsourced items must be made by the teams, not by the vendors or collaborators. Because the university teams is responsible for the upstream system requirement. Another important thing specific to university project is to keep the persons familiar with the satellite designs for operations. This is a unique problem for university project because students graduate when their time comes. To keep the personnel, the team needs to finish the project life cycles from kickoff to operation in 3 years. Because in typical Japanese universities, students stay in the laboratory for 3 years, from the 4th year of undergraduate to the end of master courses. Finally, the principal investigator, which is very often a faculty member, i.e. the professor, should be responsible for keeping the student motivation. Also, the professor should be responsible for securing the communication channels for any external assistance, because the student does not know where to ask questions and is afraid of making contact with reputable professors in other universities. One more thing about project management. It is also about safety requirement verifications. Everybody should understand that non-compliance with the safety requirement may lead to a serious schedule delay. In the worst case, the satellite is not launched and the dummy mass goes to space instead of your satellite. The picture on the right shows the dummy mass actually launched. It is recommended to list up the issues related to safety requirement and confirm with the launch providers at the end of conceptual design as well at the end of detailed design. The safety requirement verification method is agreed with the launch providers. Should be agreed with launch providers. The safety requirement verification method is agreed with the launch provider, but when you agree, you should agree on a method that can be done with a minimum effort. It should be noted the safety verification is necessary, but it is not it is a non-value added activities. Therefore, spend minimum time in a safety verification and instead do more value added activities such as mission assurance. Yes. In the mission definition phase, mission feasibility should be thoroughly checked. You should know the limit of team talent, skills, and budget when you define the mission. Also, professor is not a god. You should keep it in mind. Professor doesn't know everything to judge mission feasibility. Professor should have an open mind to suggestions, comment, assistance by others. For example, when you are building the first satellite as a team, if the mission requires 3-axis stabilizations, I strongly recommend to modify the mission. Also, if high-speed communication is necessary for a project done by students of mechanical department, its feasibility is extremely low. In the conceptual design phase, requirement management is done. You need to check the consistency between the mission requirement and the design requirement. Design should satisfy the mission requirement. If there is a design requirement, design requirement that doesn't fit to the mission requirement, then there is something wrong. One example is the case of this satellite. It used an experimental patch antenna for communication, although the mission was education. To avoid inconsistency in the requirement, an external review conducted by experienced expert is very effective. It is also important that the team, especially the principal investigator, should have open mind to external suggestions. In the conceptual design phase, a verification plan should be made. Design should not be used if it cannot be verified. Also, the verification should be doable. To have a doable, realistic verification plan, first list up the minimum test items and allocate priorities. This is a table to list minimum test items for an ISS-related CubeSat. Priority should be given to these test items marked as required. These are in this table. In the detailed design phase, risk management, FTA, FMEA are done. FTA is a fault tree analysis. FMEA is a fault mode effect analysis. The important thing is to try to minimize the risk based on priorities. Because in university satellite project, there is no resource to deal with all the risk items. External reviews are effective to list up the risk with high priority along with safety review. FTA, FMEA are often referred to as important, Yes, they are important, but we should understand that FTA, FMEA are not taught in school for most of the cases. Therefore, you should start FTA, FMEA from the levels that the student professor can understand. So do not try to follow the very detailed, very nice looking FTA, FMEA method written in a textbook. Do with your own level. List up a single point of failure and prioritize the risks. When you do this, not only part component, but also works such as long command, long assembly, and others should be considered. Because human errors are very likely in university project where many members are beginners. In the testing phase, an electromagnetic compatibility test is important. Because of the cold launch, EMC with launchers and other satellites are not important. Then what we need to verify is whether the satellite can live with self-generated nodes. We need to verify that the communication link has enough margin. Uplink signals should be much higher than the satellite-generated noise floor. This must be confirmed before moving to FM, because if the noise floor is too high, many design changes, such as antenna component layout and others, may become necessary. In the testing phase, the mission feasibility must be verified in an end-to-end test manner. As early as possible of the satellite development phase, you need to verify the basic data flow of the main mission. It is made of the following steps. Send a command uplink. Satellite does its missions, such as image capture, based on the command. Data downlink, confirmation of data, in this case image, on ground station PC. After confirming that the basic mission can be done in this manner, you can make the detail of the missions with many optional parameters. This confirmation should always be done once you move to EMs or FM phase, because this is the main missions, and without achieving these main missions, you cannot satisfy minimum success criteria. In the testing phase, the system function test is extremely important. You need to move to FM assembly as soon as FM components are delivered and start the function test as integrated system. Even if all the components haven't arrived yet, you should start from the component available. In functional test, you need to check the consistency of the data sent from the satellite, not just confirming the data came, not just confirming their data came, but check the content of the data. If there is a problem, you should not move on to the environment test, such as vibration or thermal vacuum, before you solve it. You should expect many problems to be found once you assemble FM. You need to have enough scheduled margins before moving to the environment test. For example, do not expect that you can start a thermal vacuum in 1 week after you assemble the satellite for the first time. End-to-end long-term operations is done for the 3 purposes. One is to find and fix bugs of flight software. 2 is to do operation rehearsals. You need to examine critical modes such as release, recovery from reset, and others. Nominal modes such as housekeeping data collections, and mission mode. 3 is to confirm the link budget and compatibility with the ground stations. In the link budget, line loss, noise levels inside the satellite is hard to derive theoretically. you need to confirm the link budget by testing. This test must be done by using the actual individual flight models, as the line loss and the noise level may differ depending on each satellite. Deployment test is critical considering the fact that 25% of university satellites end up DOA, dead on arrivals. One suspect is antenna deployment failure. You need to make sure that antenna can be deployed even in the worst case, which is a cold and a low battery case. When you use a heat cutter, you should have enough margins in the time you heat up the nylon wire. CubeSat may not fit into the port at satellite delivery. If this happens, it is really a nightmare. The best and simplest way to avoid is to do a fit check with an official port borrowed from the launch provider. Reason of saying official is that the slight difference in port size makes the result different. I have seen many times CubeSat fit into one port but not into another type. The fit check should be done both for EM and FM. Considering the operations of the satellite, the ground station should be prepared considering the maintenance and access. Satellite operations can be performed at any time in a day. Therefore, access to a ground station at midnight is very important. Access to the antenna for maintenance must be easy and safe. When you do operation, you need to put priorities, obtain the frequency license as soon as possible. Because at the time of launch in Japan, you have only a preliminary license obtained before the launch. You need a full license to operate the satellite officially and publish the result. Even if you have very good result, you cannot publish it without full radio license. In Japan, the full radio license is issued after confirming the two-way communication, downlink and uplink. In Japan, the full radio license is issued after confirming the two-way communications, downlink and uplink. That is established. For downlink only, it's not good. Uplink also must be established. That means the communication with the satellite is established. Also, you need to do the main mission first to try to achieve the minimum success criteria as soon as possible, because satellite can be dead anytime. And when you do anomaly investigation, never give up. The principal investigator, i.e. a professor, should keep up the motivation of the team. Also do a thorough FTA for the next project. Finally, we have arrived at the conclusions of this lecture. It is known that the University CubeSat mission success rate are low, especially for the first satellite. We can take risks in CubeSat, but this does not mean the failure is accepted. There are many lessons learned from past projects. Sharing the lessons and the root cause among the communities is important to improve the mission success rate. The Mission Assurance Handbook has been made, is waiting for the official release in 2022. We need to revise it by taking input and the new lessons from CubeSat community worldwide. Thank you very much. And if you have questions, I think you can send the questions later. Thank you.